In 1960, on the concrete apron of London Heathrow, British mechanics prepared a massive cylinder of aluminium and steel for installation. It was the Rolls-Royce Conway, built in the Midlands by an engineering culture that had defined the sound of the Second World War. But this engine was not being bolted onto the wing of a British airliner. It was being fitted into the nacelle of a brand-new American Boeing 707. This was not merely a transatlantic export order. The Conway was the first commercial turbofan engine in the world. By splitting the intake air, forcing a portion through the fiery combustion core, and bypassing the rest smoothly around the outside, Rolls-Royce had instantly made earlier, deafening pure turbojets obsolete. It delivered unmatched fuel economy and thrust, finally giving American airframes the true intercontinental range that global fleets demanded. For the engineers in Derby and the maintenance crews working on the Heathrow tarmac, the Conway represented absolute technical supremacy. They had solved the mathematical limits of the early jet age. Yet, beneath this mechanical triumph, a quiet industrial surrender had occurred. British foundries and machine shops were now supplying the heart of the very American aircraft that would soon dismantle Britain's own commercial aviation ambitions. That was the paradox of the Conway. Britain had cracked the bypass code. The engine ran quieter, flew further, and dictated the new economics of global passenger travel. But the British industry was about to learn a brutal lesson in economies of scale. Owning the invention did not mean possessing the power to control the market. But the real story of the Rolls-Royce Conway is not only the story of a technological first, it is the story of how Britain built the bridge to the modern jet age, only to find they could not afford to cross it alone. Every week, we tell the stories of British engines, factories, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place. In a Derby test facility, in 1946, the story of the Conway begins in the town of Derby in the late 1940s, inside the engineering offices of Rolls-Royce. Derby was not merely a manufacturing base, it was the foundry of British aviation power, the industrial heartland that had produced the Merlin piston engine and kept the country in the sky during the Second World War. But the piston engine era was ending. The future belonged to the jet engine, a turbine engine that produces thrust by accelerating air and exhaust gases. The early jet age was defined by the pure turbojet. A pure turbojet works by sucking all incoming air into the compressor, forcing every ounce of it through the combustion chamber and blasting it out the back as a high-velocity exhaust stream. It was a brutally simple way to make an aircraft go fast, and Rolls-Royce had mastered it with engines like the Avon. But the pure turbojet had a fatal industrial flaw. It was immensely loud, and it consumed fuel at a staggering rate. In the austere, rationing-heavy years of post-war Britain, fuel efficiency was not an environmental concern. It was a matter of strategic survival. The Royal Air Force was developing its V-bomber force, a fleet of strategic nuclear bombers designed to carry heavy payloads deep into Soviet territory and return safely. The most advanced of these was the Handley Page Victor, a sweeping, crescent-winged heavy bomber that needed to fly higher, faster, and further than any British aircraft before it. The pure turbojets of the era simply drank too much aviation fuel to guarantee that intercontinental range. Britain needed a mechanical solution that did not yet exist. The answer came from Dr. Alan Arnold Griffith, a brilliant and notoriously uncompromising aerodynamicist at Rolls-Royce. Griffith had been exploring a theoretical concept known as the bypass principle since the 1940s. His idea was elegantly counterintuitive. Instead of forcing 100% of the ingested air through the fiery combustion core, the engine would have a larger front compressor. A portion of the air would be compressed and fed into the core to be burned, while the remainder would literally bypass the core, flowing through an outer duct before mixing with the hot exhaust at the rear. This cooler, slower bypass air would wrap around the hot, fast exhaust like a sleeve. The physics dictated that moving a larger mass of air at a slower speed was far more fuel efficient than moving a small mass of air at a very high speed. It also had a secondary, almost accidental benefit. The layer of slower bypass air muffled the violent shear of the exhaust, making the engine significantly quieter. But a theory on a chalkboard in Derby was not a working machine. To build a bypass engine, Rolls-Royce could not use a simple, single-shaft layout. The engine required a twin-spool design, an internal layout using two concentric shafts, allowing the low-pressure compressor at the front and the high-pressure compressor in the core to spin at different, optimal speeds. This meant placing a rapidly rotating metal shaft inside another rapidly rotating metal shaft, all operating under immense heat and stress. It demanded unprecedented precision from the foundries and machine shops of the Midlands. The metal had to be cast perfectly. The bearings had to survive. The service network of RAF mechanics would have to learn how to maintain an entirely new architecture of power. The physical reality of the Conway began to take shape on the test stands. In October 1952, the first prototype, designated the RCO-2, was fired up in Derby. It produced just 10,000 pounds of thrust, a measurement of how much forward-pushing force the engine could generate. It was a modest figure, and the prototype was plagued by the complexities of its twin-spool bearings and internal sealing. But it proved that the mathematics of the bypass principle were sound. The fuel consumption was undeniably lower than any comparable turbojet. Rolls-Royce pushed the development forward, scaling the architecture to handle more air and more heat. By 1956, the design had evolved into the RCO-11, an engine capable of producing 17 to 250 pounds of thrust. This was the breakthrough the military needed. The RCO-11 was ordered into production for the Handley Page Victor B-2, giving the RAF the long-range strategic reach it had demanded. The Conway was officially a working piece of British defence infrastructure, integrated into airfields, maintenance hangars, and the daily routines of military mechanics. But military contracts alone do not build global industrial empires. As the Conway was being perfected for the bombers of the RAF, the commercial aviation market was experiencing a violent shift. Across the Atlantic, American manufacturers Boeing and Douglas were designing the 707 and the DC-8, the first generation of large intercontinental passenger jets. The airlines buying these aircraft had a very specific economic problem. They wanted to fly passengers across the Atlantic Ocean, from London to New York, without stopping to refuel in Newfoundland or Ireland. The pure turbojets offered by American engine manufacturers, such as the early Pratt & Whitney JT3C, were struggling with the exact same physics the RAF had faced. They were too loud for civil airports, with strict noise regulations, and they were too thirsty to guarantee a non-stop transatlantic crossing with a full payload of paying passengers. In Derby, the engineers realized that Griffith's military project was actually the exact solution to the global airline industry's most expensive problem. The Conway was no longer just a classified bomber engine. It was a product ready for export, built by a Midlands workforce that suddenly held the key to the global commercial jet age. The theory was proven on the test stands in Derby. Britain now had to convince the world that the future of flight lay not in pushing all the air through the fire, but in letting some of it slip quietly around the sides. To understand what the Rolls-Royce Conway achieved, You must stand not in a laboratory, but on the concrete apron of a British Overseas Airways Corporation, or BOAC, maintenance hangar at London Heathrow in the late 1950s. At that time, the sound of the jet age was defined by the pure turbojet. Engines like the Rolls-Royce Avon or the American Pratt & Whitney JT3C produced thrust with a violent, concentrated scream that rattled the windows of terminal buildings and shook the tools on a mechanic's workbench. They were magnificent, but they were viciously loud and notoriously thirsty. When the Conway arrived on the tarmac, the sensory experience of British aviation fundamentally changed. The Conway was a turbofan, a jet engine that moves much of its air through a large fan, improving efficiency and thrust. More specifically, it was a low-bypass turbofan. To a mechanic standing near the runway, the difference was immediately audible. The high-pitched, tearing shriek of the pure jet was replaced by a deeper, heavier roar. The physics of Dr. A. Griffith's design were acting as an acoustic blanket. By wrapping a sleeve of cooler, slower-moving air around the incredibly fast, white-hot exhaust of the engine core, the Conway muffled the violent shearing effect, where the exhaust met the static atmospheric air. This acoustic shift was driven by the engine's bypass ratio, the mathematical relationship between the volume of air directed around the core and the volume of air forced through it to be burned. In the early commercial Conway, this ratio was roughly 0.3 to 1. By modern standards, this is a tiny bypass volume, but in 1959, it was a revolution. It meant that Rolls-Royce had found a way to extract more pushing force from every gallon of aviation fuel. But this breakthrough in thermodynamics demanded a heavy price in mechanical complexity. For the service network, the dealers, mechanics, parts suppliers, and manuals that keep a machine running after purchase, the Conway presented an entirely new world of maintenance. A pure turbojet relied on a single rotating shaft. The Conway relied on a twin-spool architecture. It contained a low-pressure shaft running directly through the hollow center of a high-pressure shaft. In a British workshop or hangar, this meant that an overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards, suddenly required a much higher degree of precision. The internal bearings had to support two shafts spinning at different speeds, enduring the intense heat of the combustion chamber while maintaining perfect balance. If the machining in Derby was imperfect, or if the mechanics at Heathrow failed to align the components exactly, the engine would tear itself apart in the sky. It was a massive leap of faith for airlines to trust this unprecedented complexity. The validation of that trust came not from British aircraft manufacturers, but from the Americans. In Seattle, Boeing was trying to sell its new 707 airliner. In California, Douglas was marketing the DC-8. Both aircraft were heavy, and both were initially fitted with Pratt & Whitney JT3C pure turbojets. The American engines were reliable, but they lacked the fuel economy required to reliably fly a full payload of passengers from London to New York against the strong winter headwinds of the North Atlantic. Without a refueling stop in Gander, Newfoundland, the early American jets struggled to make the distance. Rolls-Royce offered the American manufacturers a mathematical advantage they could not refuse. The commercial variant of the engine, the Conway Arco.12, produced 1,700 pounds of thrust, yet it weighed less and burned significantly less fuel than its American competitors. The equation was simple. Lower fuel consumption meant less fuel weight in the aircraft's tanks, which meant the airlines could sell more tickets and carry more paying passengers over the ocean. The breakthrough fundamentally altered global airline economics. When BOAC ordered its fleet of Boeing 707s, it naturally demanded British power, resulting in the Boeing 707-420 series. But the true victory for Derby was the export market. Trans-Canada Airlines, Lufthansa of Germany, and Alitalia of Italy all looked at the operating costs of the American pure turbojets and chose to buy their Boeing and Douglas airframes fitted with Rolls-Royce Conways. For a brief, shining moment, the foundries and machining lines of the Midlands were dictating the pace of global transport. British engineers had successfully scaled a highly complex military bomber engine into a reliable commercial product. They had exported their physical engineering into the engine nacelles of their most dangerous foreign competitors. The Conway had proven that the bypass principle was not just a theory. It was the only logical future for heavy commercial flight. The engine had changed the mathematics of global travel. But the breakthrough had exposed Rolls-Royce to a battlefield where brilliant engineering was no longer enough to guarantee survival. By the early 1960s, the Rolls-Royce Conway had moved from an engineering experiment to an absolute industrial triumph. It was no longer just a piece of military hardware. It was the acoustic signature of British commercial ambition. To witness this peak, one only needed to stand at the edge of London Heathrow or wander through the massive maintenance hangars of the British Overseas Airways Corporation. The crowning achievement of this era was the Vickers VC10. Introduced into BOX service in April 1964, the VC10 was a heavy, swept-wing airliner designed specifically for the hot and high airports of the fading British Empire, places in Africa and the Middle East, where thin air and scorching temperatures made generating lift brutally difficult. Vickers solved this by giving the aircraft a massive, aerodynamically clean wing. But that wing required the engines to be mounted at the rear of the fuselage. The aircraft was fitted with 4 Rolls-Royce Conway RCO, 4.2 turbofans, producing an immense 21,000 pounds of thrust each. When a fully laden VC-10 pushed the throttles forward for takeoff, it did not scream with the tearing shriek of the early American 707s. It delivered a deep, resonant, ground-shaking roar. The cooler bypass air, the very principle Dr. Griffith had championed in Derby, wrapped around the white-hot core exhaust, creating a smoother, quieter departure. For the passengers inside the cabin, the rear-mounted engines meant they flew in an eerie, luxurious silence. For the mechanics on the tarmac, the Conway meant absolute pride. In the hangars, British fitters, machinists, and engineers were maintaining a machine that outperformed anything built in Hartford or Seattle at that moment. In a Britain where an aero engine could decide whether an aircraft lifted from a grass airfield, a lorry made its delivery, a motorcycle carried a rider through the night, a bus left the depot, a racing car survived the next lap, or a luxury car kept its silence at speed. Power was not an abstraction. It was metal, fuel, labor, heat, sound, repair, risk, and trust. The trust in the Conway was absolute. It was not just BOAC flying the VC-10. The Royal Air Force adopted it for their strategic transport fleet. At RAF Bryce Norton, military mechanics learned the intricacies of the twin-spool architecture, keeping the global supply lines connected. The engine was famously robust. Because the bypass air cooled the outer casing of the engine core, the Conway suffered fewer heat-related stress fractures than the pure turbojets it replaced. It could stay on the wing longer between major overhauls, meaning airlines made more money, and maintenance networks functioned with a predictable, profitable rhythm. The export market expanded rapidly. Douglas DC-8s powered by Conways were flying for Canadian Pacific and Alitalia. The Boeing 707-420 series became a flagship for Lufthansa and Air India. By the mid-1960s, the factory floor at Derby was a landscape of intense, rhythmic industry. Thousands of skilled workers, from pattern makers in the foundries to the final inspectors on the test stands, owed their livelihoods to the bypass principle. The Conway had proven that British engineering could dictate the technological direction of the global passenger fleet. The engine evolved aggressively, to meet the insatiable demands of the airlines. The early RCO-12 had delivered 1,700 pounds of thrust. The RCO-42 for the VC-10 pushed that to 21,000 pounds. Eventually, the RCO-43, the final and most powerful iteration, achieved 21,800 pounds of thrust for the Super VC-10. Every increase required the metallurgy to withstand higher temperatures, the compressors to spin faster, and the bypass ratio to be carefully managed. The physical presence of the Conway, gleaming on an engine stand before being hoisted into a nacelle, was undeniable proof that the Midlands had survived the end of the piston era and conquered the jet age. The engine was a triumph of metal, fuel, and thermodynamics. But the limits of those thermodynamics were already waiting in the shadows. The dominance of the Conway was not measured purely in thrust. It was measured in time. In the aviation business, an engine that requires frequent teardowns is a financial liability, no matter how powerful it might be. In the overhaul shops of BOAC at London Heathrow, the Conway proved its ultimate worth. The time between overhaul, the metric dictating how many hours an engine could safely remain attached to the wing before requiring a complete strip-down and internal inspection, began to climb at a staggering rate. Early pure turbojets had required major maintenance every few hundred hours, constantly frustrating airline schedules. But the Conway's cooler outer casing and highly refined twin-spool architecture meant its internal components suffered far less thermal fatigue. Soon, the Conway was authorized to run for over 4,000 hours between shop visits, a number that would continue to rise. For airlines, this was a financial revelation. A Vickers VC10 or a Conway-powered Boeing 707 could cross the Atlantic, turn around at John F. Kennedy International Airport, and fly back to London day after day with absolute predictability. The scale of Rolls-Royce's achievement began to reshape the industrial landscape of the Midlands. The Derby Works expanded to handle the global demand, creating a sprawling, deeply interconnected supply chain. Building a Conway required more than just assembly lines. It required specialist foundries pouring high-temperature alloys for the turbine blades. It required machinists working to tolerances measured in fractions of a thousandth of an inch. It required massive test cells where the engines were strapped down, run at maximum redline, and meticulously calibrated before being certified for passenger flight. Every time a Conway was crated and shipped out of the factory doors, it carried the livelihood of thousands of British workers with it. The engine had become an export powerhouse, generating vital foreign currency for a nation still recovering from the economic exhaustion of the post-war years. Alitalia, Canadian Pacific, and Lufthansa were not buying British patriotism. They were buying a mathematically superior tool for global transport, and the Midlands was the only place on Earth that could supply it. By the mid-1960s, the Conway reached its zenith with the introduction of the Super VC10. Fitted with 4 Conway RCO-43 engines producing 21,800 pounds of thrust each, the Super VC10 became the fastest subsonic transatlantic airliner in the world. It was capable of crossing from London to New York faster than any American competitor. When a Super VC10 roared down a runway in Kenya, Hong Kong, or London, the sound it produced was a declaration that Britain still held the mechanical high ground. The bypass principle had fundamentally won the argument. The future of flight was not a pure, screaming jet of exhaust. It was a carefully managed flow of primary and secondary air, a delicate thermodynamic balance conceived by Dr. A. Griffith and forged by British labor. The Conway had achieved the ultimate industrial dream. It was indispensable to both the defense of the realm and the commercial expansion of the global airline industry. In a Britain where an aero engine could still define national prestige, the Conway was a triumph of metal and thermodynamics. But that exact thermodynamic balance was about to become a trap. The first crack in the Conway's global supremacy did not sound like a mechanical failure. It did not happen on a test stand in Derby, nor did it happen in the skies over the Atlantic. It happened on a drawing board in Hartford, Connecticut, where the American engine manufacturer Pratt & Whitney decided to counter the British threat, not with elegance, but with brute industrial pragmatism. Pratt & Whitney had watched Rolls-Royce conquer the early transatlantic market with the Conway. They knew their own pure turbojet, the JT3C, was too thirsty and too loud to compete with the British bypass principle. But rather than spending half a decade developing an entirely new twin-spool architecture from a blank sheet of paper, the Americans chose a faster, cruder solution. They took their existing fuel-hungry PureJet, removed the first 3 stages of the compressor, and simply bolted a massive 2-stage fan onto the front. They designated this new creation the JT3D. It was heavier, physically bulkier, and lacked the deep, integrated thermodynamic refinement that Dr. A. Griffith had championed in the Midlands. But elegance does not dictate aviation economics. Scale dictates aviation economics. The JT3D possessed a bypass ratio, the mathematical relationship between the volume of air bypassing the core and the air entering it to be burned, of roughly 1.4 to 1. The Conway, for all its brilliance, was locked at a much lower bypass ratio of around 0.3 to 1. By pushing a vastly larger volume of cool air around the outside of the engine, the crude American adaptation suddenly neutralized the British fuel advantage. It delivered more thrust for less fuel, and because it was based on an existing engine block, Pratt & Whitney could manufacture it rapidly and cheaply. For the engineers and machinists in Derby, this American pivot presented an impossible engineering trap. The Conway was a victim of its own perfect proportions. The engine had been designed with a highly integrated core. The internal airflow, the shaft speeds, and the combustion chamber were perfectly matched to that specific 0.3 to 1 bypass ratio. If Rolls-Royce wanted to increase the size of the fan to compete with the JT3D, they could not simply bolt a larger fan onto the front. The high-pressure core of the Conway was too small to drive a massive front fan, and the internal shaft dynamics were not designed to handle that kind of aerodynamic load. To beat the Americans, Rolls-Royce would have to redesign the entire engine. The very thermodynamic balance that made the Conway so incredibly reliable, the feature that allowed it to stay on the wing for over 4,000 hours in bivouac service without an overhaul, now made it physically inflexible. It was a masterpiece trapped in its own geometry. The shift in the global market was swift and ruthless. Boeing, which had happily built the 707-420 series around the Conway to secure international sales, quickly offered the JT3D to its customers. The American engine was cheaper to buy, heavily supported by a vast domestic parts network, and offered the range required for transoceanic flight. Almost overnight, the export orders for British-powered 707s and Douglas DC-8s dried up. Trans-World Airlines, Pan American, and other global heavyweights chose the domestic American option. This was the cruel reality of manufacturing costs and economies of scale. An engine could be beautiful, durable, and historically important, yet still lose if the component cycles and manufacturing agility of a rival moved against it. Pratt & Whitney had an enormous domestic military market funding their development, allowing them to amortize the costs of the JT3D across hundreds of airframes. Rolls-Royce, relying on the much smaller British domestic market and the dwindling RAF bomber fleet, simply did not have the capital to fight a war of attrition. The Conway was suddenly isolated. Its survival now depended almost entirely on the Vickers VC10. But the VC10, despite its elegance and its popularity with passengers, was a heavy, expensive aircraft designed for short, hot runways in the fading outposts of the British Empire. Global airlines did not want an aircraft tailored for high-altitude African airports. They wanted the Boeing 707, which was optimized for the high-volume routes between New York, London, and Paris. As sales of the VC10 stalled, the demand for the Conway stalled with it. In the maintenance hangars at London Heathrow, the British service network continued to treat the engine with absolute reverence. The mechanics knew they were working on a machine that rarely failed, a power plant that had taught the world how to cross oceans quietly. But outside the hangar doors, the industry had bypassed them. The engine still worked perfectly. The industrial war it was built to win had already been outsourced to the other side of the Atlantic. The retreat of the Conway from the global commercial market was not an overnight collapse. It was a slow, mathematical strangulation. In the boardrooms of BOAC and the government offices of Whitehall, the economic reality of the Vickers VC10 was becoming impossible to ignore. The aircraft was beautiful, and the 4 Conway engines at the rear made it a passenger favorite, but it simply could not match the seat-mile costs of the American Boeing 707, powered by the Pratt & Whitney JT3D. When the state-owned British airline reluctantly began canceling its later VC-10 orders in favor of American aircraft, the Conway lost its primary commercial lifeline. Rolls-Royce attempted to pivot. They applied the twin-spool bypass principles of the Conway to a smaller, more efficient engine called the Spey, designed for short-haul passenger jets like the BAC-111 and the Hawker Siddeley Trident. The Spey was highly successful, keeping the Derby production lines moving. But the transatlantic heavy market, the prestigious arena the Conway had effectively invented, was slipping permanently out of British hands. By the late 1960s, the aviation market shifted again, and this time the scale was terrifying. Boeing announced the 747, the first wide-body jumbo jet. It required engines with thrust ratings approaching 40,000 pounds and a massive bypass ratio of 5-to-1. The Conway architecture, with its narrow core and 0.3-to-1 bypass ratio, was completely useless for this new era. You could not simply scale it up. The internal thermodynamics were mathematically locked. To stay in the global race, Rolls-Royce had to abandon the Conway lineage entirely and begin developing an entirely new, incredibly complex high-bypass turbofan known as the RB2111. This was the ultimate tragedy of the Conway. It had proven that the turbofan was the only way forward, but competing in the high-bypass era required a level of financial investment that was unsustainable for a private British company. The development of the RB211 was so technologically punishing and the manufacturing costs so catastrophic that it pushed Rolls-Royce into receivership. In 1971, the British government was forced to step in and nationalize, the process where the state takes ownership or control of a company to prevent its total collapse. The Aero Engine Division. The company that had built the Merlin and the Conway was effectively bankrupt, crushed by the financial gravity of the very technological arms race it had started. As the company reorganized under state control, the physical presence of the Conway began to fade from the world's major airports. The early Boeing 707-420s and Douglas DC-8s that had proudly carried British power across the Atlantic were slowly sold off. They found second lives with charter airlines and freight operators in South America, Africa, and the Middle East. In the maintenance hangars, the service network began to shrink. Parts for the twin-spool core became harder to source. The foundries in the Midlands were no longer pouring castings for the Conway. They were entirely consumed by the desperate effort to make the RB211 work. Overhaul intervals, once the absolute pride of BOAC, became increasingly expensive as the supply chain contracted. When a secondary airline mechanic needed a replacement turbine blade or a specialized seal, they increasingly had to cannibalize older, grounded engines. Furthermore, the regulatory environment was shifting. While the Conway was quieter than the pure turbojets it replaced, it was still a low-bypass engine. As airports like London Heathrow and New York's JFK introduced stricter noise abatement rules in the 1970s, the deep, tearing roar of the Conway became a legal liability. The engine was increasingly restricted, fined, or banned from operating during night hours. When a Conway-powered airliner finally reached the end of its economic life, the end was undignified. At aircraft breakers' yards, the once revered power plants were unbolted from the wings, drained of their remaining oil, and left sitting on rusted engine stands. The aluminium casings, which had once represented the absolute pinnacle of British precision machining, were eventually cut up for scrap. The manual pages detailing the exact tolerances of the twin-spool bearings were thrown into the bins of aviation history, rendered obsolete by the massive, quiet turbofans of the new wide-body era. For the British mechanics who had learned their trade on the Conway, the engine's twilight was deeply frustrating. They knew the block was still solid. They knew the thermodynamics were still sound. But a commercial aero engine cannot survive on engineering elegance alone. It requires a continuous flow of capital, factory tooling, noise certification, and airline fleet orders. Without them, even the most reliable engine eventually becomes too expensive to maintain. By the late 1970s, the roar of the Conway was largely confined to the Royal Air Force. The military kept their fleet of Vickers VC10s flying as strategic transport and aerial refueling tankers, preserving the sound long after the commercial market had abandoned it. The military mechanics at RAF Bryce Norton became the final custodians of Dr. A. Griffith's vision, keeping the complex architecture alive through sheer dedication and a dwindling supply of factory spares. But the commercial airspace belonged to the Americans. The high-bypass turbofans from Pratt & Whitney and General Electric had taken control of the transoceanic routes. The British invention had been overtaken by American scale. The engine still ran. The orders slowed. The American factories moved faster. The bypass ratio moved on. The sound faded. The badge remained. The sky it conquered was gone. The Rolls-Royce Conway did not survive the brutal commercial realities of the 1970s, but the technological principle it proved became the undisputed foundation of modern global aviation. Rolls-Royce, as a company, barely survived the transition. After the crushing nationalization of 1971, the process where the British state took ownership to prevent a total collapse of the aero engine division, the Derby Works were forced to abandon the Conway's fixed, low-bypass architecture. They took the painful, expensive lessons learned from the Conway and poured them into the RB211, which eventually evolved into the Trent engine family. Today, those massive, high-bypass British turbofans dominate the skies, powering everything from the Airbus A350 to the Boeing 787. The Conway was the necessary, brilliant sacrifice that allowed the Midlands to learn how to build the future. In Britain, the physical sound of the Conway was preserved for decades not by the commercial airlines, but by the Royal Air Force. While BOAC and the global carriers scrapped their Boeing 707s and early Vickers VC10s, the military kept their specialized VC-10 fleet flying as strategic transport and aerial refueling tankers. At RAF Bryce Norton in Oxfordshire, generations of military mechanics and fitters treated the twin-spool engine with a mixture of reverence and frustration. For them, the Conway was not a museum piece. It was a daily reality of dripping oil, complex bearing alignments, and meticulous inspections. They kept the global supply lines connected, relying on dwindling stocks of factory spares and old, oil-stained service manuals. Because of their stubborn dedication, the deep, tearing roar of 4 Conway engines launching a heavy tanker off a wet British runway remained a part of the national acoustic landscape all the way until 2013, long after the commercial world had gone quiet. Today, the preservation of the Conway has moved from the active tarmac to the static, hushed halls of British institutions. At places like the Brooklands Museum in Surrey, the RAF Museum in Cosford, and the Imperial War Museum, Duxford, the massive cylinders of aluminium, titanium, and steel sit on heavy engine stands. Enthusiast groups, retired BOAC mechanics, and aviation historians still pore over the surviving parts catalogs, tracing the incredibly precise tolerances that Dr. A. Griffith demanded back in the 1950s. They preserve the memory of a time when the British maintenance network had to learn an entirely new language of thermodynamics to keep the country in the air. This is not nostalgia. A Rolls-Royce Conway sitting under museum light is a physical argument about a specific moment in industrial history. It proves that there was a time when a British engineering firm could fundamentally alter the mathematics of global travel. Before the Conway, commercial flight was a screaming, fuel-thirsty luxury that struggled to cross oceans reliably. By proving that the bypass principle, forcing a sleeve of cool air around a burning core to generate thrust and save fuel, was mechanically viable, the Conway built the bridge to the modern world. Every time a modern passenger boards a wide-body airliner, they are relying on the exact thermodynamic theory that British Labour proved in the Midlands over 6 decades ago. As a surprise footnote to its legacy, the Conway's accidental byproduct, its quieter acoustic signature, actually helped shape modern urban geography. By proving that a jet engine could be muffled by its own bypass air, the Conway laid the mechanical groundwork for modern noise abatement rules. It proved to regulators that massive international airports like London Heathrow could expand without completely deafening the cities that surrounded them. The tragedy of the Conway was never a failure of engineering. It was a masterpiece of mid-century thermodynamics. Its twin-spool architecture was a triumph of Midlands machining, and its reliability in the hangars set standards that the rest of the world envied. But the Conway stands as a brutal reminder of the forces that govern the British engine market. It proved that an engine could be mathematically perfect, historically important, and universally respected by pilots and mechanics, yet still lose its world because of manufacturing costs, competitive scale, and the relentless pressure of global supply chains. The engine had taught Britain to trust a new kind of sound, but it had not solved what would happen when that sound became too expensive to adapt. Pratt and Whitney and Boeing did not beat the Conway with better theory. They beat it with volume, flexibility, and the harsh realities of commercial economics. The Derby factories moved on. The mechanics who once knew the Conway's internal bearings by heart have largely retired, their knowledge fading into archival memory. What remains is the metal itself. Somewhere in a British aviation museum, an old Rolls-Royce Conway still sits on an engine stand, the complex aluminium casing dulled by time and dust, the original badge still proudly visible on the front, waiting in absolute silence for a sky that the new industry no longer needs it to conquer. See you in the next one.